Today we will be dealing with a tank problem, as these things are commonly referred to in differential equations. In our case, we will be modeling the carbon monoxide levels in a room that has a leak spewing into it with a 5% concentration of carbon monoxide, along with an initial concentration of 0.001% carbon monoxide for the air in the room itself. In addition to finding an expression for the volume of carbon monoxide in the room as a function of time, we also wish to determine when the concentration of carbon monoxide will reach 0.015%. Finally, we will determine what the concentration of carbon monoxide will look like in the long term. Our dimensions are 10 by 15 by 8 feet, making for 1,200 cubic feet altogether. Assuming an initial concentration of 0.001%, we have an initial volume of 0.012 cubic feet of carbon monoxide in the room. For our purposes, x of t will be the volume of carbon monoxide in the room as a function of time. We will assume a single flow in and a single flow out of the room. Since the total volume of air in the room is constant, the same volume will be flowing in as flows out. As previously stated, the air leaking into the room has a 5% concentration of carbon monoxide. However, the concentration of carbon monoxide flowing out of the room depends on the amount present in the room at time t. At this point, we need to know how many cubic feet of carbon monoxide are flowing per minute both in and out of the room. Multiplying the total airflow into the room by 5 parts per 100 gives us 0.006 cubic feet per minute. For the outflow, the volume of carbon monoxide flowing out of the room each minute is equal to the total air flowing out, 0.12 cubic feet per minute, times the ratio of carbon monoxide to the total volume of air in the room at time t. This simplifies to x divided by 10 to the 4th minutes. From here, we need to take these in and outbound flow rates and combine them into an expression for the derivative of the volume of carbon monoxide present in the room with respect to time. Now we have something that looks like a linear first-order differential equation. If we move the term containing x of t to the left-hand side, then we find that we can use integrating factor to solve for x in terms of t. For those of you new to integrating factor and would like an extra example of this technique, I will link to a previous episode where I use it to solve for the flight time of someone jumping out of a plane using a parachute. Our task will be to calculate mu of t. Since p of t is a constant, the integral is pretty straightforward, and the term in the exponential works out to t divided by 10 to the 4th minutes. When we insert mu of t into the aforementioned formula and integrate both sides with respect to t, the dt's cancel on the left-hand side, and we are left with the integration constant c sub 1. On the right-hand side, we pull out the constant 0.006 cubic feet per minute, and we are left to integrate a simple exponential with the constant multiplied times t. Upon integrating this, the exponential remains the same, and we divide the quantity by a factor of t from the exponential while adding the integration constant c sub 2 to the right-hand side. At this point, it makes sense to simplify the bookkeeping by combining our integration constants and allowing c to equal c sub 1 minus c sub 2. From here, if we divide both sides by the exponential, we now have an expression for x in terms of t. We can also cancel out the minutes terms in the remaining constants in the first term on the right-hand side, and voila! The room has a volume of 0.012 cubic feet of carbon monoxide in it at t equal to 0, and we can use this fact to determine the value of the integration constant c. T equal to 0 renders the exponential equal to 1, and c can now be calculated by subtracting 60 cubic feet from both sides. Now that we have an expression for x in terms of t, we can use it to determine when the carbon monoxide levels will reach 0.015%. We begin by calculating the volume of carbon monoxide when this happens and equating it to x of t. Also, here I use the notation T sub 1.5, and I apologize if that's a little bit confusing. Now for the fun part. 0.18 cubic feet amounts to the target percentage, and we're going to start by moving 60 cubic feet on the right-hand side over to the left. We can then divide both sides by negative 59.988 cubic feet. Multiple terms cancel out, and we're left with a positive number on the left equal to an exponential on the right. Taking the natural log of both sides, we can eliminate the exponential on the right, and we're left with negative t sub 1.5 divided by 10 to the 4th minutes. From there, we multiply through by the appropriate constants, and we have a figure that tells us when the carbon monoxide will reach 0.015% concentration. Amazing how the satisfaction of grinding out an answer makes all of the noise outside seem to go away for a moment. But we need to focus on the future. So what happens to this room if we just let the leak keep going? The answer is actually quite intuitive, especially if you think about the mixture of the air flowing in. But we love math here at Pentagram Prime, so let's reduce this whole thing to a limit. As t approaches infinity, the second term in x of t will tend towards 0, and we are left with 60 cubic feet of carbon monoxide in the steady state. If you go back and crunch the numbers, you will find that this works out to 5% of the total volume of the air in the room, corresponding to the percentage carbon monoxide of the air leaking in.